Hello and welcome back. So let's keep working and computing the forces, and actually we already work how to compute the forces, so hopefully it's everything clear now how to compute forces in Paraview. As I mentioned, any solver will give you all these forces, so here's just out of curiosity you want to know how to do it in Paraview. Now the last part that I would like to address is how to compute moments. So here we have how moments are computed. So we have done the most difficult part, which is computing the forces. Now the moment is simply this cross product, okay, that you have a position vector and your forces vector. Okay, so you have two vectors. Your output will be a vector. Yes, the order is important. Depending on the order, you get a different sign, but doesn't matter. But I don't want to go into details. Just go and do your mechanics books and you get all these equations. So basically this is what we have. We already computed forces, give a reference vector. This one is the reference point, so you want to compute the moments in all points in the surface, and reference to a given point can be 0, 0, 0, 1, 0, 0, 0, whatever you want. Okay, so this is what we're going to do. Finally, also to close, regarding for those using OpenFOAM and compressible solvers in OpenFOAM, remember that the pressure that you are solving is the modifier pressure. So it's the pressure, actual pressure divided density. Okay, so this is not Pascal unit, something else. So you will need to multiply your pressure by density to get the right units. In the case that we're working, I'm assuming a density of 1, so it doesn't make any difference. So be careful about this. Same applies for wall shear stresses. You need to multiply that by the density only for incompressible solvers in OpenFOAM. You are using Fluent, CFX, everything is okay. I don't recall the Star CCM, I don't know any other solver, so I'm focusing on just these two. So yeah, that's all. So let's compute moments. So I will go, I already have it here open. So this is how to compute moments. Honestly, I tend to do things super complicated. So you will have now in the cases you can in this state to reproduce this one, but it's pretty much the same. The new step that we have is the moments, and by the way, also moments we computed in the points in the vertices, okay, because we need to get cell centers. It's a little bit tricky, so it's easier to go and compute everything in the points. So what we did the last time for forces that I was working, I like to work in cell centers, just move it to points and that's it. So let's do all the steps, okay. So let me launch here, and I will open the OpenFOAM dataset. Okay, so let me go here. So remember, since doesn't change, it's pretty much the same. Okay, so let me go here, open, and put it here. So in the video description, you should have the link to download everything. Okay, so we have our data set. All the data is in the cell centers. Remember, you can just move it to two-point data. So you have this filter here and apply pass cell data, and now you can have everything in cell centers or points. Okay, it's up to you. I like to work with cell centers. So the next step, so let me go. So when the Windows opens here, okay, let me change here. Okay, so yes, so what we want to compute all the forces, everything. So I have here filters. So let me go here, the shortcut here, and I want to extract a block. I just want the pipes, the walls. Okay, so I see that I already have all my fields there. I converted to cell points, so you have everything. Okay, remember the trick for velocity. In this case, we don't need velocities because we already have pressure and we have wall shear stress at the wall. So now to compute the total force, it will be the summation of these two. Okay, we also need the normals because we need to project it in our reference system. So let's compute normals. So search surface. So here will give me it shaded. So if you click there, it will tell you that it must be BTK. So the BTK, remember, is this easy trig extract surface, and that's all. You will have it in BTK. Now surface normals. Okay, no, filters will be surface normals here. So now we have surface normals. I want also in cell center. So at this point we have everything, normals in cell centers and points and all the other quantities, okay? So at this point, the next step that we need to do, okay, I have cell size also, because I need the area. Remember to plot in the surface, we need the area to get the right forces unit, okay? Because you get pressure, let's say pressure in Pascal, but that is not the pressure distribution. You need pressure times normals times area to get your pascals, okay? So you have a filter here, the Newton, sorry. Surface filters and cell size, and I just want the area, okay, put your area there. So cell size will be area. It is only cell-centered data. Again, if you want it, if you want this data, point data, just add another filter, so I don't overcomplicate things, and you will have it there. So point data or cell A data, it is pretty much the same. So now that we have this, let me go back here to recall the steps. Okay, we can do the calculators, and we have total there. Okay, so let's do the calculator. So apply this calculator. So you can go point or cell data. So let me stay in point data. I will call it total, and it will be this one. So pressure times normals minus wall shears. Be careful about the sign notes, and it depends on reference system using. It's also in OpenFOAM it's minus. Okay, so I put this one now because if you put it 0 will be only that contribution. Okay, so that just to enable one or the 7. But look at that, what we have here, it is Pascal. Wall shears, stresses, and pressure are in Pascal. So if you want to get total force, that's what I call it total, not total force, because this is not, okay, your total force. So leave it like this, and we have the point data, and this is total. So now if you go and compute the integral of this, you will have the force, and the integral multiplied by the area, summation, and so on. But if you want to plot now the force distribution, okay, I will call it total force. Let me go here, let me take this, let me put it here, and I multiply all this stuff by the area, and let me go area, you have it here, and now this will be the proper units in Newton. So what you are going to see here, total force, okay, this is a force distribution in your pipe, which is very different. Let me split my screen here and put here this one from total, which is the distribution of pressure plus wall shear stresses, not in forces units. Okay, so now if you want to compute the total force, you can do the integral here or the summation of this one. It's up to you. Just to remind you, as we did it previously, you have integrate variables, the integral there, and it is point data. Okay, so previously it was working cell data, now I move to point data, and where do I have is total. Okay, so here you go. So if you compare with your forces, okay, you have fluent and OpenFOAM. Okay, so OpenFOAM this plus 2 will give you this plus 2, this, and so you have here influence. So as you see, correct results or very similar. Okay, and then if you want to use this one or the total force, remember it's the summation, so you have that Python calculator. I'm not going to do it. So now let's move to moments. Okay, so let me apply another calculator here to compute moments. Okay, so let me go here. So this is the difficult part, getting the forces. As soon as you get the forces, the rest is very straightforward. Okay, so here we have moments, and just to display. So we go, and I will go, and I'm working, let me put moment, same idea, okay, moment, but it is not the actual Newton meters, okay, because you don't have Newton units, you need to get here total force, okay, the actual units, the actual quantity. Why I'm putting point data and not say that cell data, because cell data, you don't have the coordinates. Okay, so you have it just in point data. However, what you can do, and let me go here, is to overcomplicate things as you do it, but you can get the coordinates of the cell center. So you have a filter called cell center, okay, then the calculator, and then move the cell centers to point data to cell center, and you get it, okay. But to overcomplicate things, actually, in the state files you will get that, and then you can do your operations. But at this point, I think it's easier to stay in point data. Okay, so you get the moments, remember, and we go back here. It is the cross product of two vectors, so force and position vector. So here you have your total, okay, which is not the force, is the total. And then this is your position vector. So here, 0 hat plus 0 j hat k hat. Here I am assembling a vector, and this is the vector of the reference point. Okay, I want to compute moment about a reference point, and it's 0, 0, 0. So if you want a different point, you put here 1, 0, 0, or whatever point you want, okay? Minus coordinates, okay? And here you will get the distribution around also. Just to make clear, the first part here, I hat, j hat, k hat is to assemble a vector, and this vector will represent your reference point. It's 0, 0, 0. So you want something else, just put 1, 1, 1, or 1, 0, 0, 1 pi 10, whatever you want, okay, minus coordinate. So apply, and you will get this quantity here. I call it moment, okay, so here. But again, remember, this is the distribution, not just the total, which will be the pressure plus shear stresses. It's not the complete stuff, okay. So if you want to have now the right moment distribution, you need to multiply by the area, okay, to get the right unit. So let me go back here, and what was that? Okay, calculator. So here you see I have it there. So let me put another calculator, and this one we'll call it moment total, okay. And then see that it's very much the same. Total times your or you can put here total force will be pretty much the same, okay. And that's it. Okay, so we have it here, and we can move it total and see that you have the distribution. So now if you want to get your moments, you go here, filters, and integrate variables. Let me close this and apply, and there you go. We have the integral point data, and I only want to see how I call that. I call it moment, and let me put this here. Okay, so you have moment, and here also in your data you're going to have this file where you have all the moments. So you have Fluent and OpenFOAM, okay, so as you see, pretty similar. And again, you have pressure and viscous contribution. So look at that. We have here the moment, this one around. So you will have X, Y, and Z, okay? So X, Y, small values, and Z is the one that gets similar, okay, it's okay. Then look at that, we go to total, what is the summation of the forces, now just to demonstrate that you have here the totals, everything, and that's it, okay. So there you go, how to compute moments, okay. You do your integral, okay, be careful about what you're using, so integral here. So to show you, for instance, let me go back to total, and let me put to 0 the wall shear, so put this 0, and it is corrected there. So, and we can go back, and the viscous component for the pipe or the pressure component, okay, you have it there, minus 12, okay. So see that around this one is the largest. Then here you will have some differences, okay, how things are integrated. Pretty much you have the same, here you have pressure and viscous component. So look at that, the pressure component minus 1293, okay, and then you have the other two. So see that it's closer, okay, so this is OpenFOAM. So see that the data sets flew in OpenFOAM, slight differences. So let's focus that we have OpenFOAM, okay, very close, and also very close. And now let's take a look at the viscous component. Okay, so same stuff we do. So we were here, and let's put this one 1 and this one 0, apply, and there you go. You have your forces, and then you go viscous, voila, you have it there around. So this is moment, viscous moment around X, Y, and Z, which is the largest one. And then you can go here, and that's one to get the total. Just go back here, 1 and 1. And this is it. So this is it, how you compute forces and moment. Remember that, for instance, here you're multiplying by the area. So if you want to get it from here, it's just the summation. So put that Python calculator, which I think I put it here. Yeah, you have here in Python calculator. So here you have all the workflow. So here I'm comparing all the moments, all the computation. So summation of the force total should be equal to the others and so on. So you have all your operations here and the moments and so on. So this is it, okay? This is how you compute your forces and moments in OpenFOAM. As I say at the beginning, I don't see any reason why to do it. You get that from the solver, but the only reason now that I can say that, okay, you need to do it in Paraview is just if you would like to plot your forces on the surfaces. It's the only reason that I can see now to do this. So, and then probably also if you want to do cut planes and plot on those lines the forces distribution, as I mentioned, is you have winds and the span-wise distribution of lift and so on. So that's the only reason, but for the rest, is you are just interested in total forces, just rely on your solver, okay, whatever you are using. This is it, okay, and pretty much it works the same for unsteady data. So probably we'll prepare another case, take a case on steady, but it's exactly the same. So thanks for your attention. Hope you found this useful. Thumbs up if you like it, and if you didn't like it, I don't accept negative feedback, but now just drop your comments in the description, and that's also. Thank you, see you next time, and bye.